Okay, it's time to start. Let me very briefly tell that this guy doesn't need an introduction. He's our research coordinator, so very well known for all of us. And he has been so kind as to give a talk on his science, despite the fact that he has now a lot of extra duties that have to do with the fact that he's organizing how we behave, basically. So, Javier, I think it's your time to give the talk.
let's continue. And you see that this object is rather big. It's 0.5 kilometer in diameter. So this is a very dangerous one. It's not the great destroyer, but if an object of half a kilometer impact the Earth, there will be a global event that will have a strong effects, probably destroy completely our civilization if it happens. Right? And it will not destroy the whole the life of most of the life on Earth, but will have strong consequences. The shape is called a spinning top shape, is like a diamond, and this is due to the structure. I will explain immediately, and also the structure and the fast rotation rotates once every 4.3 hours is the cause of this shape. This is the orbit of Bennu. Okay, you can see it's an orbit with a semi-major axis very close to 1 that crosses the Earth and has a small inclination. A small inclination respect to the orbit of Earth is critical to decide to go to an object, because the lower the inclination, the easier to send a rocket to, and the cheaper to send a rocket to an asteroid. Not only that passes close by, but also that the inclination is low, because when you send a rocket, you use the velocity of the Earth. So if you change the inclination, you have to add a lot of fuel to change the inclination of the movement. The shape is due to fast rotation and the internal structure. Most of the asteroids are the product of collisions. Collision, at the beginning we have some very big protoplanetesimals, let's say 100 kilometers to 1,000 or so, but these planetesimals started to collide between them and in the early ages of the formation of the planets. Right? In particular, the presence of Jupiter excited the orbits in the region between Mars and Jupiter. That's why we have this main belt asteroid, this main ring of asteroids. And one of the things that happens during the collision is that a lot of material reaccumulate and form new bodies, smaller bodies, new bodies that has a very porous structure, and if you put this porous structure and make it rotate very rapidly, the shape that attain is like this material that move from the poles to the equator, and this is something that has been observed in several asteroids. For example, this is Steins, one of the asteroids visited by Rosetta during his flight to Churyumov-Gerasimenko. Here a comparison of the shape of Bennu with well-known buildings. And what we know about the properties of Bennu are that it is a carbon-rich asteroid. Carbon-rich asteroids are the most primitive ones. And these asteroids are the parents of the carbonaceous chondrite meteors. That are meteors that are barely processed. In fact, chondrite is a body that contains chondrules. The chondrules are these spheres here, like this, that are composed of different minerals that were produced in an early phase of the sun that produced a heat wave that impacted the protoplanetary disk. This melted material, calcium, lithium, and other materials that formed these spherules, and then these bodies formed, accreted into a small asteroid, or into an asteroid, following a structure like the one we see here. That is, it is like to take sand on the beach and compact it a little bit You do not melt the materials. You do not produce strong metamorphosis processes, but compact them and have the structure of these chondrites. And some of these chondrites contains carbonaceous materials. This is one of the typical carbonaceous chondrite meteorite, the Murchison meteorite. It's called a CM type. In Murchison, you can see a lot of chondrules here, and in a structure that it is the structure is weak. This kind of meteor has lost most of the material during the entry on the atmosphere. It's not like metal meteorites that preserve a large fraction of the original body of the meteoroid that entered the atmosphere. Carbonaceous chondrite lost more than 90% of the material during the entry, the interaction with the atmosphere. But in these objects, we found two things. We find water in the structure of the mineral. We have what we call hydrated minerals, a lot of them in the structure of carbonaceous chondrites. And we found complex organics like alcohols, carboxylic acids, sugars, and in particular, we have found different amino acids in this kind of meteorites. So, considering the history of the Earth, on the formation of the Earth that formed with a very wet material, material with no water at all, that was very the temperature of the Earth was very high when collapsing. This carbonation material cannot survive the process of formation of the Earth, and also it is likely that the Earth has no water at the beginning. So the water we have and the organic material we have in the surface of the Earth likely came from small bodies of the solar system, comets, and this kind of primitive asteroids. So those objects are very important to understand the history of the life on Earth. And we know that they came from the carbonaceous chondrite came from what we call primitive asteroid, because we can compare the spectrum in the laboratory of a carbonaceous chondrite like this one with the spectrum of an asteroid like this one. That is obviously the noisier one, and they are very similar. So we can.
For those of us who don't know much about this, can you explain what is a primitive asteroid and how do you know it's primitive?
Immediately. Let me continue. The nature of we know that they are primitive because of the spectrum. We qualify we taxonomically qualify the spectra. We show later, and then we compare with the meteorite that are pieces of asteroids with the spectra of meteorites, and then we can have a correlation between the kind of meteorite and the kind of asteroid we see in space. So this is a comparison between the spectrum of a meteorite, a carbonaceous chondrite, and the spectrum of what we call a primitive class asteroid, and we see they are very similar. And as I said, most of the material is destroyed during the entry in the atmosphere. So if you want to study the weakest material in a primitive asteroid, we need a sample return mission to do that. In fact, the solar system formed, as we all know, from a big dust and gas cloud that collapsed, formed the sun, a disk around, and in this disk, the accretion processes formed what we call planetesimals, or the primitive asteroid, some of them big enough with the sufficient mass to differentiate, some others that don't have enough mass to have a process, an important process of differentiation. These are the most primitive ones, formed probably in a region, not in the very inner, but a little bit farther from the sun because they contain water. In particular, carbonaceous chondrite contains water. So to incorporate water to the structure, you need to have ice and no gas, right? And then the collisional history of the asteroid produced an object like Bennu, that it is an aggregate of small parts, and then the rotation produced the shape that we see it as it is now, right? Then you have in the main belt collisional families, and we know they are collisional families because they have similar orbits. A lot of objects with similar orbits and similar spectral properties are produced by the impact of a larger one. And these collisional families scatter objects to the inner main belt, as I will show you in the next slide. And so to know the origin of Bennu, where do Bennu come from, and to be able to incorporate the detailed information on Bennu to the big picture of the asteroid, we need to study the collisional families in the main belt, in particular the primitive one, and that is why we run the PRIMAS spectral survey. What is the PRIMAS spectral survey? PRIMAS is an observational program inspired in a paper we published with Campins in 2011 about the origin of Bennu and the spectroscopic properties of Bennu. And we aim to characterize, in particular, the population primitive families in the inner main belt. These four are the first one we started to work, and because they are the more likely sources of asteroid like Bennu, and we use to do that visible and near infrared spectroscopy, basically using GTC, TNG, William Herschel, and at El Roque de los Muchachos, but we also use some other telescope that the IRTF, you can read it here, the IRTF and the NTT and the SOAR telescope also. And the question we want to answer is, where do Bennu and Ryugu came from? Going to the primitive asteroid. How we know that this is a primitive asteroid? We take the spectrum. Typical spectra of asteroids are shown in this plot. This is in the visible wavelengths. This is the reflectance. Basically, to obtain the reflectance, we take the spectrum of that asteroid, the spectrum of a solar analog star, and the ratio between these two spectrums is the reflection of the light by the asteroid. It's the reflectance. Usually we normalize the reflectance as a certain wavelength, and this show different kind spectral type of asteroids. This is a type of a spectrum called B-type with a very big absorption band centered at 0.9, that it is produced by basaltic materials. This is the typical S-types. S-types has a band centered mostly in the 1 micron band, and this is the product of minerals like pyroxenes and olivines that are rather processed minerals. And on the other hand, you have those ones that they have only a weak or no band in the 1 micron region, and usually, mostly they are or neutral or red. I mean, this reflects less light in the blue and more light in the red part. So this is a red object, but with no features or very weak features. These objects are called the primitive ones because they are related to the most primitive meteorites. The spectra is similar to the most primitive meteorites, and in particular, Ryugu and Bennu are part of what we call the C complex, that it is related to the primitive asteroids that are mostly in the inner and mid main belt, while the objects like these ones are related to comets and objects in the outer main belt and beyond. This is the spectrum of Bennu. It's more than neutral. It's slightly blue. It's a B-type asteroid in part one of the subclasses of the C complex. This is spectroscopy and photometry. So we know that Bennu is a primitive asteroid. And as I say, we will study the primitive families in the inner main belt. This is a plot of the main belt and beyond, because we go up to the Trojan asteroids, semi-major axis versus inclination, and you can see that the main belt is structured. There are several regions that are depleted of asteroids that are called the resonances. We have the mean motion resonance and secular resonances that are due to the dynamic, the interaction with Jupiter and Saturn, basically, that make that in these regions, the asteroids are removed very rapidly from there. And some of the asteroids that are removed from there are injected to the to the planetary region, inner planetary region, and produce a group of near asteroids that I said have very unstable orbit and survive very in a short time in this region. Of the orbit, with respect to the ecliptic. These are orbital parameters, semi-major axis and inclination of the orbit, right? In fact, what we will study are collisional families in this region. How we recognize collisional families? Here you can see the eccentricity versus semi-major axis and the sign of the inclination versus semi-major axis. This is a kind of orbital parameters that are not the actual ones, but the ones you retrieve as constants during long periods of time. I mean, the orbital parameters change because this is not a two-body problem; it's an n-body problem. But these parameters oscillate around some values, and these are the kind of orbital elements considered to look for clusters. There are several clusters of groups in the main belt, and these groups are what we call the collisional families, right? Because these objects are likely produced by a collision of a larger one and retains information or retain memory of the orbit of the primitive body, or the original body, or the parent. And we plan to study several families, in particular Lepolana eulalia, that is the biggest one and the most important. This is a complex. Some authors think there are two families here and not only one. Erigone is another very important family, Sulamitis, Clarissas. I mean, in the space of orbital parameter, they form clusters that can be recognized, and the dynamics is recognized very well. And when we study the spectral properties of this object, we recognize that they are similar. In fact, we've been obtaining a spectra of the parent bodies of the largest body of each family. The Sulamitis family, for example, is the name of the largest body, that is 762 Sulamitis, the asteroid. And you can see that all these objects, none of them have the band at 1 micron, that typical of the rocky asteroids. And in general, they are part of the C complex, almost neutral to slightly blue spectral slope. What we measure here is we obtain the taxonomical type. There is a taxonomical classification of spectra. In the C class, you can have different kind of subclasses of C classes, of C-type objects. We derive the taxonomy. We measure the spectral slope, and we also look for hydration band. For example, you can see here a weak, very weak, and band that extends from almost 600 to 800 nanometers, and this is associated with hydrated materials. So this is associated with the presence of water in the asteroid, right? Not water in form of ice, not liquid water, but water included in the minerals. And this water is very important because to be included in the mineral, to incorporate to the structure of minerals, and at a certain time in the parent body, in the protoplanetesimal, before all the collision happened, something warmed the asteroid, maybe some radiogenic materials, and in the interior you should have some liquid water during a certain time that interacted with the mineral and incorporate to the structure. So this is very important to trace the thermal history of the system and the formation history of the asteroids. We published several results on some of the family. We observed 65 asteroids in the Polana, 100 in the Eulalia, about 20-something Polanas in the near-infrared, 64 and 33 Clarissas in the visible. And we also have impressed a paper that resume all the results and link the families with Bennu and Ryugu, and we have several other families in preparation, with papers in preparation. We are using mostly the GTC for doing these studies. We are taking advantage of the poor conditions. When the weather is not that good, we have a program that uses this kind of time that is useless for other programs to observe our 20 magnitudes to 18, 19 magnitude asteroid. And we are doing this large survey. In fact, this is the only large survey devoted to primitive asteroids, as far as I know. And we characterized, we already characterized 4 families, the Polana Eulalia, with different spectral. This pie diagram shows the different kind of subclasses. The B type, the C types, the X types. Those are slightly blue. C types are almost neutral, and X types are slightly red. Those are the mean spectra of the different classes in the Polana Eulalia. This is the case of Sulamitis, right? And Erigone. You can see in the case of Erigone clearly an absorption band around 700 nanometers, indicative of hydration. I mean, this kind of a study, and this is the distribution of the slope, and we can see that on one hand we have two families that have a similar distribution of the slopes, mostly B types, almost a little bit blue, negative slope is blue, right? And the others, Erigones and Sulamitis, have a similar distribution of slopes. And we also, as I say, studied this hydration band. Using the spectra, we met the depth, the central band, and we were able to detect, for example, in the Erigone, that the Erigone family, one half of the objects the observer present this absorption, while in the Polana Eulalias only one. So we have a family also of objects that are hydrated and the other that are not hydrated or less hydrated than the other. In fact, we found that we have two kinds we have two groups of families up to now. We are observing more, but we have this with no absorption band and almost blue, and those that are slightly redder with a wider dispersion of spectra in terms of slopes, and that present this hydration band. All these helped us to identify which are the families that are likely the origin of Bennu and Ryugu, and also to study what we expect to see in the surface of the asteroid. Notice that those asteroids are formed by the reaccumulation of material, and the original body can be differentiated in some way, not in a differentiation like in Earth with the heavier materials in the interior and the lighter in the exterior. But for example, if they hydrated, the hydration didn't happen in the whole asteroid, but in a region, in a layer in the interior of the asteroid, where the water can attain the liquid state, right? So when you destroy this in the same family, you can have dehydrated and hydrated asteroids, right? And if you make an asteroid composed of pieces, right, that reaccumulate, you can have some hydrated parts and unhydrated parts. Remember that what we see is the whole asteroid, the light from the whole surface of the object. So we only have one spectrum. But when we go to an object and look at close by it, we probably see different regions of different composition in the asteroid. These are the spectra of Ryugu and Bennu compared to the spectra, the B-type spectra, both are B-types, and compared to the B-type spectra observed in the family with their 1 sigma dispersion. And we concluded that they belongs to the Polana-like family, and they probably come from the Polana Erigone or Clarissa family. So we know that we already know that Bennu is a carbon rich, that is the parent. That is a parent of carbonaceous chondrites. So bringing material to Earth is very important because it's the only opportunity to study this weak pristine material that do not survive the entry to Earth's atmosphere, and that may contain the precursor of the origin of life and the Earth's oceans. And as Bennu is one of the most potentially hazardous asteroids, OSIRIS-REx will determine the physical and chemical properties of Bennu, which is critical to plan missions to develop any kind of impact mitigation or on the destruction or deviation of the orbit of a Bennu-like object. So the objectives of OSIRIS-REx are to return and analyze a sample of Bennu surface, map the asteroid, completely chemically and mineralogically map the asteroid, document the sample site, also to measure the orbit deviation caused by non-gravitational forces. Non-gravitational forces are very important, not only to accelerate the rotation of the asteroid or decelerate, and also to change the orbit. In small objects, let's say less than 10-15 kilometers, a torque appears when you illuminate the object by the sun. The absorption of energy of the light. This introduces a torque, a small torque in one direction. But when the asteroid remit, do not remit this energy in the same direction, but in a slightly different, because it rotates. Depending on the orientation of its rotation, it will increase or decrease the semi-major axis of the object. And this is very important. Understand this effect, that it is called the Tchaikovsky effect. Is very important to predict the evolution of the orbit of an object like Bennu, and this is very important to predict if it could impact or not in the future. And also because can be used to deflect the orbit of the asteroid, but this is another stuff. And finally compare the observed with ground-based. The spacecraft. This is OSIRIS-REx. It's a 6 meter by 2.5 and 2.5 meter spacecraft that weighs about 880 kilograms with no fuel, but with fuel it attains the 2 tons that, as I say, is in flight to Bennu. It will arrive to Bennu in October. And the payload is composed of these instruments, 5 to make remote observations and 1 to take the sample. We have visible cameras, a laser altimeter, a thermal emission spectrometer, a visible and infrared spectrometer, and this experiment to study the regolith. Those 5 are to remote observations, so to attain these objectives of the mission. And the mission was selected in 2011, when at this moment we've been invited to incorporate to the science team. And in 2016 was launched from Cape Canaveral. was a very exciting moment. I never think that it can be so exciting to be in a launch of a rocket. And this moment you really realize that if this something wrong happens, the work of several years of a lot of people just disappear. So we've been there. We've been invited to the mission. This is Julia. This is myself. This is Noemi Pinilla, my wife, Noemi's husband, and this is Humberto Campins on the way to the launch place where the place we saw the launch. In 1 year later, when the object approached Earth again, it has a Earth gravity assist maneuver to change the inclination of the orbit and send it to the orbit of Bennu. And something very important for us, during this maneuver that passes through below the South Pole, below Antarctica, once the mission passed, they pointed the instrument to Earth and took some images and spectra, and the important thing is that everything is doing well. So this was another critical moment, and in fact those images are being used to make the first calibration, the first in-flight calibrations. The science observations during the asteroid, during the mission, will start in October 2018, a little bit before we will have some first images, but not really the science ones. And we will have several phases. The first is the preliminary survey, with the spacecraft still rather far from the object. We will be able to take images of the whole asteroid in only one image, and it will be used to search for asteroid plumes. As I said at the beginning, some primitive asteroid present some activity, cometary-like activity, so we will look for any possible cometary-like activity in Bennu from before arriving. This can change a lot of stuff. If Bennu is ejecting dust, the dust can affect the mission. So we have to take care of this. Also, we will look for natural satellites, small ones. If it formed just aggregating collisional pieces of an asteroid, some of these pieces can be orbiting the asteroid, or also the process that formed the strange shape of Bennu can also produce not only material moving from the pole to the equator, but also material can be ejected and stay. And this is a way of forming binary asteroids. There are a lot of binary asteroids all around. And we will use these observations to measure the Yarkovsky acceleration, obtain the first asteroid shape. I will show you how important is this point for us, the shape model. Do a inside rotational characterization and a global surface characterization. Then we will move closer to the object, and in this period, the flight dynamics team will change. The mission will, instead of using the stars, they will start to use the features on Venus surface to navigate. And also we will use these images, of course, for doing science. And during the tail phase survey, we will be observing Bennu with all the instruments. This is the critical phase for us. Most of the science is going to be done here. We will have a detailed spectral, thermal, and geological map of the object. Then we will be even closer to Bennu and start to inspect in the last phase, in the last science phase, remote science phase, and start to inspect and select the sampling site. We need to select some places that can be used to take the sample of the asteroid. The most important things in this case is security. You will see at the end of the talk the complex maneuver to return the sample of the object. So we will have all this time until until 2020, right, to do to obtain the images, to do science, and then we will concentrate on the selection of the site and the sample collection of the object. We are involved in the OCAMS camera. That are 3 cameras. MapCam is the most important for us. It's a medium field imager. It has only something like 4 centimeters lens, so it's very small. It's a Galileo-like telescope, right? Then Polycam, this is a small telescope. It's like a Celestron 8 telescope, more or less, right? It's a Ridge-Arquettian, very small one that will study details on the surface in the science phases, not when we will too close. When we go too close, we just cannot focus this telescope. Remember that we do not put a focuser in a telescope in space, right? The less moving parts, the better. And there is a very small camera here. It's like a webcam or something like that. That is important during the phase. We are very close to the asteroid to put to put in context the sampling site during the close approach. MapCam is a small camera that produces a 4 degrees view with a resolution of 1 arc-minute. That has 4 filters. This is important for us. That that allow us to sample the colors of the object, and we'll look for satellites and outgassing plumes. We'll monitor the rotation of the asteroid, map the asteroid in 4 different colors, and this data is going to be used to do the asteroid shape model and the photometric model, apart from the study the mineralogy and of the whole object and the detailed images of the sampling site. Why and what is our contribution? Our contribution is in the study in the color ratio or in the color maps of the object, and this is something that it is completely different to whatever I did in the past. We are not dealing with the flat image. We are dealing with the image of an object that has a shape, and this is very complicated. And in particular, what we are going to do with the colors is to make a diagnostic of the composition of the asteroid surface. That is also related to the size distribution of the regolith. We can also see these different regions with different ages, and then we can study the effects of space weathering. And so this will be a complement of the spectral data, but the spectral data, the advantage with respect to the spectral data is the space resolution. We will have a much higher space resolution. In fact, during the detailed survey, we will map 80% of the surface with an accuracy and a resolution smaller than 2 meters. While during the reconnaissance phase, we will observe 80% of a region around the regions. We will sample we will take the sample with a resolution smaller than 50 centimeters. And what we want to measure, what we want to see from these color maps? Those are the filters we are using in MapCam, and this is the spectral, typical spectrum of a primitive asteroid. So we will be able to reproduce not the spectrum, but some spectrophotometry in 4 bands, in 4 regions, and this region can allow us to obtain this spectral slope, and this absorption is also related to hydrated materials. We will be able to measure the visible slope. Changes in visible slope also are indicative of changes in composition or in the shape of the regolith. We will be able to look to see if there are some deep absorption band in the 700 nanometer. This filter is specifically centered to look for the hydration band. So this will help us to identify regions with different composition or age. I'll try to go fast. We need to do that. We need to have a very good shape model. This is the kind of shape model that's dividing the structure in triangles. And this is very important because this is not a flat object, and the observations are done in different observing conditions, different geometries. So each part of the asteroid reflects the light with a different incident and viewing angle from the observer. So this change not only the illumination but the geometry, and you need to have this asteroid shape model that it is produced combining images and the LiDAR, and produce also photometric model to properly calibrate the images. You need you observe maybe from an inclination, and then you need to map the asteroid and combine images that, for example, here we combine two images that are observed in different geometric conditions. So you need some software, and there is a software used by the spacecraft that correct for geometric variation, but for doing that you need a very accurate shape model, right? Well, and you need also to correct the illumination, because you have shadows, the different areas do not receive the light of the sun in the same inclination. So there are photometric models that include the effect of phase angle, that is the angle between the observer, the sun, and the sun object observer in the angle, and this changed with each phase of the model. And this is a disk model correction. So you have the phase function and the disk function. You can resolve this if you have tons of data. If you have hundreds of images and each image corresponds to a different triangle of this shape model that had thousands of triangles, you have 100,000 data of each point, and you can analyze this to resolve these equations. And this is one of the things that Juan Luis is doing. He's been reproducing the photometric calibration of the dawn images of Ceres, and he's doing it very well. In fact, his corrections are even better than the one already published in the case of Ceres. Well, this is a fitting of data, and this is the uncorrected image with a lot of shadows and different region that looks of different albedo, and once you correct photometrically, you have a very flat image, and probably these details are below the resolution of the space of the shape model, so you cannot correct inside the triangle what's going on. You also do spectrophotometry. The dawn cameras have 7 filters, and we are analyzing these Ceres images in preparation for Bennu. And you can retrieve the albedo at different wavelengths, or the I over F, that it is the illumination you measure divided by the flux, some flux received in the filter, right? And you can produce spectra normalized at a certain value. This is normalized in this filter and shifted to see the clarity. So you can recognize here regions of different spectral properties. This is the region in red is redder than the region in this region in blue, that it is here in black. And we reproduce it, first reproduce it using images obtained from the PDS, the measurements by Schroeder et al. And we noticed that there are some difference. We contacted Schroeder. We decided to do not use the PDS calibrated images, but take the raw ones and recalibrate from the starting. This is from the beginning. This is rather complicated for sure, but he's doing it very well. And this is the difference he found between the PDS images, and the images corrected by us. And that's, this is very much similar to what Schroeder measured. Notice that we have some variation here. the Schroeder images are flatter. So we are now obtaining better results thanks to Schroeder. And we plan to analyze the images using a clustering technique. For example, applying the clustering technique to a region of the Occator crater, the crater with the bright spots in series. The clustering technique was able to recognize different regions that are real different regions, because they are not just points spread over the whole image, but concentrated in surface structure. This is the region considering the brightness, and this is just the spectrum, right? Well, he is improving this since the beginning. Studied different regions of series, and in some of them just we didn't see any different in the spectra, but in the case of Occator we see not only brightness but spectroscopic difference. These are the spectroscopic difference and so on. So to finish, we are preparing ourselves to use MapCams, analyzing images on series obtained by other spacecraft. We will study what happened with the 700 nanometer iteration band in this we obtained from the clustering, and we are also able to reproduce the photometric correction, so we are ready for Bennu to provide the mission the photometric corrections. Finally, once we did all the science and select the sampling site, the mission is going to take a sample. This is the last thing I will show you. To do that, OSIRIS-REx has an arm, like a few meters arm, with a collector at the bottom that make a touch and go maneuver. It will stay a few seconds, just come very slowly, touch the surface, blow air on the surface to enter, making the regolith to enter in the collector, and then use the arm to impulse itself and leave the target. This is a video. This is, I promise, is the last thing with the touch and go maneuver. This is the collector, and what I say, we will go very, very slowly close to the object. We can do this 3 times until collect at least 60 grams of material. The goal is 600 grams. Then nitrogen is blown, and the material goes into the capsule. Has some filters to select some particular sizes, and then use the arm to impulse itself and leave the asteroid, and only turn on the thrusters when it's far to do not affect the asteroid. Put the sample in this capsule, and then start to stay some time around the Bennu, and in 2021 start to come back to Earth, arrive to Earth 2023, and this capsule, it sends this capsule to Earth, this cone to Earth with a parachute, and if everything goes well, we will be able to have a sample of primitive material to be studied in the laboratories. Sorry for the time.
So it's kind of late, but I'm gonna ask for a couple of quick questions, and keep in mind that there is coffee served in the library in case you wanna continue the discussion. So.
So what is the angular size of Bennu right now?
From where? From Earth? Oh, it's sub-arc second. Sub-arc second. It's only 500 meters, and actually let's think it is about, let's say, half an AU, half an astronomical unit. Well, during the close approach, it's larger, but it is sub-arc second in any case. It's too small.
I'm curious about the kind of material you want to come back from the regolith. I mean, you mentioned that most of the matter in the, for example, in a normal meteorite coming, going through the atmosphere, loses 90% of the. But even so, in Markinson, for example, we have a lot of amino acids, no?
Well, we have a lot of amino acids in the strongest structural material of the
So
meteoroid.
What do you expect will it be different in the in Bennu?
Well, the experts on this laboratory study expected to find much more materials that are lost, simply lost. The weakest one didn't survive. Maybe even some water ice or whatever. We really don't know what we are going to see there.
First one, has somebody observed the asteroid in high spatial resolution with a high spatial resolution instrument, adaptive optics, something
No, the highest
to
resolution.
make easy the topography from Earth?
No, as
like
I
that.
said, the shape is very small, and only radar data can resolve the asteroid from Earth. Was able to resolve it. I don't think you can see much. Maybe during a very close approach, but in this case you have an object that it is moving extremely rapidly, that it is not too bright, rotate too fast, but it's not an easy task.
This is the very last question, because as I said, there is.
We are late, so my fault.
The sample return mission, the sample return will take from the uppermost surface the sample. Don't you expect that this will be modified in some way by solar wind, by all the radiation, and not be that representative in the end than something a bit more, even a meter deep interior?
Yeah, the expectation, the space weathering supposed that affect only the first millimeter layer. And if you see, we will blow. It's not just to take what it is in the very surface. You will be able to retrieve material that it is a few millimeters below. We will not make a drill. No? Unfortunately, we don't have a lander to do that. But we expect that we will have some material, some weathered material and unweathered material, or much less weathered material. But it is true, the cosmic ray, the high ultraviolet radiation from the sun, and also the micro collisions transform the materials in the surface of the asteroid. This is something that it is well known, and we expect to have some less or few little weathered material in this maneuver.
So I really think that we have to stop here because we had time to discuss later. That's what I was insisting. So thank you again.
Thanks a lot, and sorry for the